Right, well, let me just briefly say, principally to the people who are here with me in the room, but not forgetting those who have chosen to join us remotely. I say welcome to the Birmingham Centre for Rail Research and Education here in Birmingham. That is. Hi. Hi.
Sounds like Godfather.
Hi.
Yeah, you know, he's got a very thick English, or he's got a very thick accent.
Have I got a very thick accent? Once again, I'm hearing voices that may not be intended for us. Please check you've got your mic muted. So, other than welcome, the only other thing that I have to say is that so that other people can benefit from this, we are recording this session. So, if you ask questions at the end, you will be on. You will be able to record your voice. I hope that's okay. If it isn't, there's not much I can say other than don't ask any questions. All right. That's all I have to say. I will be back. But Marcelo, I'll hand over to you now. No, Marcelo. Marcel. Confusing.
Okay, thank you, Bruce. Bruce asked me to introduce to you the speakers of today's meeting. So welcome to this special monthly meeting from INCOSE Transportation Working Group, INCOSE UK RIG and APTA SE Group. It's called Systems Thinking for Systems Engineer. And today we have three speakers. The first one will be Professor John Elphick. He is from Royal Academy of Engineering Visiting Professor of Railway Systems Integration at the University of Birmingham. He is a respected and dedicated professional engineer who has a track record of delivering value in complex and challenging environments. He has 25 years experience in control systems and railway, including heavy rail, metros and trams. John has made significant technical and leadership contributions to railways around the world in areas of assurance and integration, digital transformation, command and control system design and delivery, remote monitoring and asset management systems, cybersecurity, passenger information systems and rolling stock. As head of Solution Integrated Assurance and Safety for East-West Rail, John has led change in approach, establishing a collaborative and pragmatic approach to integration, assurance and approvals or governance. The second speaker will be Dr. Marcelo Blumenfeld. Dr. Marcelo Blumenfeld is an assistant professor in future transport systems at the University of Birmingham, leading research and capacity building that look at the introduction of new technologies in transport systems to contribute to Sustainable Development Goals, SDGs, especially in the Global South. Internationally recognized expert, having acted as a consultant to leading organizations such as the United Nations, the World Bank, GIZ, FCDO, and national governments of Thailand, Ethiopia, and Brazil. Highly multidisciplinary scholar with research portfolio of more than £750,000 and over 10 years experience in projects that involve operational optimizations, horizon scanning, systems engineering, and systems modeling. The third speaker of today is Dr. Bruce Elliott. Dr. Bruce Elliott joined the University of Birmingham as an associate professor in rail systems in 2021 after a 40 years career in industry as a software engineer, systems safety engineer, and system engineer, mostly in the rail sector. More than 30 years he has been engaged with trying to improve engineering processes as a consultant, as a researcher, and as a teacher.
Excellent. Thank you, Marcel. Can everyone hear me okay? Can you hear me online?
Yes, affirmative.
Yes, we can.
Thank you. So good afternoon, everybody. My name is John Elphick. Thank you for that introduction, Marcel. I am delighted to be presenting to the RIG. And once again, it's been many years since I presented to the RIG, so it's lovely to be back here. And also, it's great to be talking across the world to TWG and the APTA communities. I'm very proud to be presenting with Marcelo and Bruce, two good friends of mine, and we're going to be talking about a subject which is, I think, both exciting and very interesting. So without further ado, let's get started. I need to press that one, presumably. Does that work? It doesn't work.
It doesn't work. Or you go through.
No. There we go. Okay. So systems thinking. So in a virtual room of systems engineers, why do we want to talk about systems thinking? We're all experts in systems engineering, and so why systems thinking? Bruce and Marcelo and I have observed over the last few months and years we've been working together, there's an awful lot of talk about systems thinking at the moment in the rail industry. Lots and lots of people talking about it, lots of great pictures, lots of worthy concepts being talked about. But actually, we've detected there's not that much in terms of sort of rigorous process and academic basis for it. What is it all about? We've included a couple of examples up there. The top one is the Institution of Civil Engineers SED process. That's taking a systems approach to infrastructure delivery. You can look that up. It has some fantastic imagery and pictures. There's also the Royal Academy there, the Royal Academy of Engineering in the UK. They brought together a panel of experts this summer who were talking about how to solve wicked problems using systems thinking. But neither of those things and many of the other similar things that are out there in this industry, none of them talk about some of the rigorous techniques, some of the academic techniques that we're going to introduce you to today. Press the right button. There's also lots and lots of very disparate views out there. You can search the internet and find all sorts of stuff. I just picked this one. One gentleman here was talking about some important concepts for systems thinking, and the response that he got in LinkedIn was somebody decided that all systems thinkers need to know is about knowledge graphs, full stop. So you've got huge desperate, it's really, really simple. Just learn this one thing. That's all you need to know. And then you've got other people writing, huge volumes and all sorts of information about it. So what are we trying to achieve? What are we really at? In addition, we also observe that actually after sort of a significant amount of time spent, cost and effort put into systems engineering in the railway, the results are perhaps patchy at best. Systems engineering has been applied in railway infrastructure projects, certainly in the UK, probably for the last 25 years. Bruce and I were both involved in the start of the Rail Interest Group for INCOSE some 20 odd years ago. And yet we've got situations where the results still aren't brilliant. One example here, there's a Department for Transport paper report here from 2019, where they talk about the fact that systems engineering, systems integration is a key problem that needs to be solved, that needs to be addressed in terms of delivering better infrastructure projects. And they've looked at big projects like Crossrail and the electrification of the Great Western Main Line in the UK. Mark Wilde also talks very eloquently about Crossrail. There's lots of information about his lessons learned from Crossrail. He talks about the fact that everybody in a project should truly own the whole. And he does provide that talks about some commercial levers that you can pull to achieve that. But he also talks about making sure that you keep things simple, managing complexity, being transparent. These are quite kind of fluffy concepts. I don't know about you, but sometimes I find that a little bit insulting, because I've never worked with an engineer who came to work and tried to make things complex, or tried to not manage complexity, or tried to be opaque or secretive in what they were doing. You know, we all try and do these things, and yet somehow it's just, you know, it's still not quite working. We also see in this world where everyone's talking about systems thinking that actually some commentators and some engineers actually conflate systems engineering and systems thinking. And so really, Marcelo and Bruce and I started a piece of work a little while ago thinking about, well, what is it? We decided to educate ourselves, and we don't pretend to be experts in this, but we've spent some time trying to understand what are the academic basis of systems thinking? What's it really about? I will admit, we all admit, we've been very heavily influenced by the work of Professor Mike Jackson, who's an emeritus professor now at Hull, and this very weighty but very good book that we would recommend you to recommend to all of you. What we conclude, having looked at this, is that systems engineering is actually just one part of systems thinking. Systems thinking is a broader church. And what we think is that, and this very much chimes with where Mike Jackson is that systems engineering is necessary but not sufficient to fix some of the problems that we face today and the problems that we're going to face tomorrow. And therefore, that's really what motivated us to try and to put this lecture together. Mike Jackson, similarly, he spoke to the UK Annual Systems Engineering Conference last year and challenged the systems engineering community to arm itself with some of these other techniques that we're going to talk a little bit about today, in order to be able to tackle the problems which, in his words, systems engineering struggles to tackle on its own. So that's the sort of background. That's why we're here. That's what we're going to talk about. What we're actually going to cover, so in the next 40 minutes or so, we're going to cover 4 techniques and give you a little bit of an idea of where you might use them. This is going to be a real canter through. You're not going to be, you know, hopefully we're going to whet your appetite and want to go and learn a little bit more, but we're going to talk to you about soft systems methodology. I'm going to talk through that. Marcelo is then going to talk to you briefly about systems dynamics and the viable systems model. And then Bruce will talk a little bit about system heuristics, critical system heuristics, and some summing up comments. So we've put these into a little bit of a timeline just to try and orientate things for you, so you get a sense of where things are. Systems engineering, you're all familiar with. I mean, the roots of that, perhaps you can argue, started in the Second World War. We've identified the seminal work in the Bell Labs around the 50s, which was probably key in terms of some of that development, and then the amazing work on the Apollo missions, which really rooted systems engineering in terms of a key way to deliver complex problems. And then that's continued through and is obviously still much talked about now. The other techniques we're going to talk about, you'll see that there was a big explosion of work in the 50s and 60s, lots of work on systems thinking. We'll talk a little bit more about some of those images and what happened there. Largely, perhaps other than the systems dynamics, most of those techniques, to our understanding, have largely fallen out of favor in the 21st century. We're certainly not aware of much use being made of these techniques, certainly in infrastructure and rail projects. We would very, very much like to know if we're wrong. One of our motivations for talking to you is to find out more. And our research suggests that these things aren't widely used. Our hypothesis to you is that they probably should be. So let's move on now. So now I'm going to talk to you a little bit about systems, soft systems methodology. Soft systems methodology is the brainchild of an engineer who worked for ICI in the 60s and 70s, called Peter Checkland. Peter Checkland was a systems engineer. He understood systems engineering, and he tried to apply, as he was promoted through the ranks in ICI, he had tried to apply systems engineering to more management problems. And he left ICI in the 70s and moved to Lancaster University. And that was really because he started to realize that systems engineering doesn't really work when you apply it to management problems. These messy, wicked, difficult people problems didn't work. He calls them soft systems as opposed to hard systems. And this led to the birth of this soft systems methodology. The seminal book probably in this area is his book, you can't quite see, Systems Thinking, Systems Practice, released in 1981. And that led to a number of other books, one of which, wrong slide, too many computers, one of which I used an image from here, Learning for Action with Checklin and Poulter in 2006. One of the things I love about Checklin's books, and I would recommend them to you, is that he uses pictures in a fantastic way. We talk about pictures it says 1,000 words. But I love the fact that when you read his books, he often illustrates the points he's making. And I think this image, taken directly from one of his books, really captures this idea that's at the heart of soft systems methodology, which is that hard systems thinkers see the world as a mechanism, a sort of Descartesian or Newtonian mechanism. So observer number one, who's your kind of classic perhaps systems engineer, is looking at that system and he's saying, I see a system which I can engineer. You can draw a boundary around it. A system is, the world is a system, and each system has subsystems, and each subsystem has subsystems. That's the worldview. That's the way that they're thinking about it. Whereas a soft systems thinker, observer two, is seeing a really messy world, a world where there's complexity and confusion. And what he's saying is, I spy complexity and confusion, but I can organize the exploration of it as a learning system. So soft systems methodology was about bringing a systematic approach to the way that you learn about a complex environment, as opposed to assuming that the thing you're trying to engineer is a system of systems. So soft systems methodology, the most common thing you'll hear about it, or one of the key things, is that it's built on the idea of the fact that different people have different worldviews. Weltanschauung, the German word for a worldview. And this is really core to the academic rigor that's underpins soft systems methodology. We all look at the world based on our experiences and our learning. For example, if you think about infrastructure projects, you could take two people, perhaps live in the same village, live in the same family, look at HS2. They both have the same information, they both know the same data, they're both experiencing that project in the same way, but you'll have one person who's a supporter and one person who's against. So they're looking at the same world, but they're seeing a different thing. They're interpreting it in a different way. And the fact that people have different worldviews is key and core to soft systems methodology. Checklin came up with a 7-step model, which I don't have time here to go through all of the steps, but in essence, you start up here with a problematic situation. So something which is a problem. And the first step is that you then try and explore and understand that problematic situation. And this is where you'll begin to unpick the fact that probably at the core of your problematic situation, you're going to have different people with different worldviews. You then move into the systems thinking world, and you use some techniques that he's developed that allow you to understand and document the different worldviews. And you then move back into the real world, and you use that understanding of the different worldviews to try and come up with a solution or a way of changing the system, which everybody thinks is a positive step forward. It's not about solving the problem. It's about finding a resolution that everyone agrees with, is at the core of soft systems. We know of one use of soft systems in the railway, which was an MSc project in Birmingham here, which successfully used it around asset management of lifts. again, as I said, we would love to hear from you in the questions at the end if you know of other uses of soft systems. So finally, I'm going to finish off with a quick example of one part of the soft systems methodology. So if you imagine an example where we've got a Caribbean island, whereby we've got a problem because that we've run out of runway space. All of the American tourists, well, it's got a growing tourism business, but the American tourists want to arrive on a Saturday afternoon, and the runways reach capacity. You've got some people in the island who are saying, actually, we need to expand the airport. We need more runway capacity. You've got some people who are saying, actually, this is, we don't. If you build a bigger runway, you're going to tear down more forest. That's really bad for the island. What you would do in the first step, second step of soft systems is draw a rich picture. A rich picture has no syntax. There's no right and wrong way. And that's one of the things that everyone who I've talked to who've used this and myself, one always feels uncomfortable about that, because we like syntax and rules as engineers to help us, the guide rails help us feel comfortable. But actually, the whole benefit of this is to let everyone collaboratively draw what you feel, draw what you see. And there's no right and wrong. And we're capturing here that some people are saying that tourism is the lifeblood of their island, and some people are saying that tourism is destroying their island. So you've got two conflicting views there that soft systems would perhaps help you to begin to resolve. So soft systems is something that you would use where you recognize you've got those multiple stakeholder views. You've got people who agree that something's not right, but actually they probably can't agree on what is not right. So they certainly can't agree on what needs to be done about it, because they can't even agree on what. And it helps you resolve or find solutions in that environment. That's a really, really quick hurdle through that. I'm now going to hand over to Marcelo, who's going to talk to you about system dynamics and VSM. That
will be interesting. Thank you very much, John. Just confirming that people online can hear me. No, well, in the room, yes, but
yeah.
Okay. So thank you very much, John. I think that the first part of SSM is really interesting because it kind of portrays and emphasizes the complexity of systems, of real world systems, and how it's not always a straightforward way to navigate it, and there is no optimal way. You can always have right answers, but there is not necessarily one single answer to a complex problem. So I packaged it next to techniques or methods. Even though they look different and they look at different aspects of complex systems, they have something in common, that they both draw from cybernetics, which is one of the roots of systems methodologies, into those management or structural aspects of complex systems. And interestingly, the creators or the people who came up with them were also engineers who started looking at non-engineering problems. So I think there might be a pattern, but we might discuss that later. The one I start with is the one that probably people are more aware of, which is systems dynamics. Even if you haven't heard the name, you might have seen it, but now you're going to associate the method or the technique with the concept behind it. So systems dynamics is the brainchild, if we can say, to Professor Jay Forrester from MIT. Interestingly, the history of system dynamics might explain a little bit of what is behind that. So Jay Forrester was in MIT, and he was working during the war in cybernetics, in silver machines, things like that part of electrical engineering. And later on, he started getting this interest he started to observe the problem of management and corporate issues, and he saw that there was a way of applying those techniques into those management problems or more complex problems. And that's what he did. So coincidentally, MIT was starting the Sloan School of Management, so there is probably a lot of coincidences there. So he had a first project with General Electric, and General Electric had an issue. So they had a lot of staff turnover in one of the plants, and they thought it was because of external factors of business, business cycles and things of the sort. And so what he did, he was very interested in that, and he started using stock and flow simulation and stock and flow models, which is one of the system dynamics, one of the ways of dealing with systems dynamics. And he managed to see that it was actually an internal issue of the structure of the system that was creating those cycles, rather than something of external forces. And that led him to think, well, there's something here, right? So this was his realization that the structure of a system is equally important to the components within it, because the structure of a system will dictate the behavior of a system. And that's kind of the foundational premise behind systems dynamics. It's looking at those non-linear feedback loops that will dictate what the system will do in the end. So he wrote a book in '61 based on that work with GE called Industrial Dynamics. Oh, there was some, hopefully nothing, that I'm not saying anything that is absolutely wrong. Another coincidence is the person that occupied the office next to him was, after he wrote the book on industrial dynamics, so he was looking at those cybernetic principles into industrial problems. Coincidentally, the person that occupied the office next to his in MIT was the former mayor of Boston, John Collins. And they started talking, and there was quite an interest in applying system dynamics into a grander problem of cities. And he wrote urban dynamics, so he started applying the same concepts of cybernetics, looking at this nonlinear behavior of complex systems, which is based on the idea of feedback loops. Feedback loops is that you have an interaction, and sometimes the interaction will feedback something to it, and the feedback will control then what the interaction represents. And that worked really well with the book. So there was another organization, Club of Rome, got to him and said, let's do something even bigger. And they wrote word dynamics. So let's simulate the word. So this is another thing that was quite critical and unique to systems dynamics, is that it's even from industrial dynamics to the word dynamics, it's very much based on computer simulations. So they use computer-based simulations. What happens is that I'll go to the next slide and explain a little bit why. It's because in complex systems, there is a limit on how much we can understand of a complex system by ourselves without the help of computer simulations. Because you can observe some interactions, some causal loops, and some feedback loops by themselves. But when you have 500 of these, you cannot understand all the indirect relationships at once. So you need those computer simulations to run those feedback loops together. And this is what really drove that work in system dynamics and the word dynamics. So they were running word simulations based on key inputs and outputs. There are two techniques within system dynamics that are widely used, as I mentioned. So there are causal loop diagrams, and they have this systematic feedback process. From this very kind of honest approach that you cannot model the entire complexity of a system from the top down, what you do is you go the other way around. So you start creating a web based on direct feedback loops between key elements of a system. And once you start building them together, then you start having the complexity that emerges from that. And if you have that simulation from that model, you can actually predict the behavior of your system. That is one of the key premises of it. And on the other side, you have stock and flow diagrams. That was what Jay Forrester used with General Electric. The only difference that stock and flow diagrams have to causal loop is that they differentiate what are stocks, what are the key things, like the parts of your system, and what are the flow and the things that change it in the system. But there are also ways of it. Of course, there is not enough time to cover, but it's a very interesting technique / method to simulate the behavior of a complex system that has multiple causal relationships under certain changes, you know. And I think the important thing is because we all know from complex system, there is the emergent behavior and there is the unintended consequences of a system. And this is the premise of system dynamics, is to anticipate them and see if you can predict what happens from a complexity, from the complexity of systems once you are creating changes within. But yes, so unfortunately, this time I'll go to the second one, which is, oh, sorry, I forgot there was an example. That is my fault, but I think the example is really good. This is an example based on that airport story that John was talking about. If you think that you have the challenge of the airport and the runways, then if you start creating those causal loops to understand what will happen with the changes that that process will create, you can start thinking what will happen with the system itself, because you understand the structures that are within it. So you might have some balancing behavior, which is, for example, one key element is balancing the other. So because you have congestion in the airport, you will have a limit on the number of flights. So it's never something that you can do. But you might also have some reinforcing dynamics here, that you have more tourists, you have more money from tourists, more investment, and that is a reinforcing feedback loop. But that helps you paint a picture of this very complex system to try and understand and predict what will happen with the changes that you might install in it. Now going to the second one, which is also rooted in cybernetics. So it's also rooted in the trying to understand the structures of a system and the impacts and influence that a structure of a system will have on a complex system. But from a caveat, that VSM, Viable Systems Model, is interested not necessarily in the behavior only, not necessarily that much in the behavior, but in the adaptability of that system to external changes. So this is the crucial difference. And Viable Systems Model, brainchild of Stafford Beer, Professor Stafford Beer, it was interested in cybernetics as well. And the same path went from cybernetics into management. So he actually was pioneering this management cybernetics field. And one thing that I found fascinating when going deeper into VSM is this concept that Stafford Beer created of the purpose of a system is what the system does. Because I think a lot of us in systems engineering and engineering, we think you can design the purpose of a system. But if you think about how the structure of a system will dictate its behavior, and the behavior might not be what the system was designed initially to do, you start understanding that the purpose of a system is that it's actually what it ends up doing. So this is the key idea behind that. And also, if we're talking about similarly about grand desires and grand ambitions, is that in 1971, the President Allende of Chile invited Stafford Beer to use his viable systems model to create a national model of governance for the country of Chile. So talk about ambitious endeavors. And they started to design it. They started to design, but in 1973, many of you might know, Chile had a military coup. So the project went to a halt and never returned to it because Stafford Beer changed directions in his life quite a lot since then. And the premise, I will have an example in the next slide of how it works. But the key thing that I believe, and I honestly believe, I think it's underutilized. VSM is underutilized. There is a lot of potential for us in transport, for us in these complex projects that we find in transport, because transport is intrinsically complex. To understand that within a system, there are different systems with different functions. And you need to understand the functions and what the functions and the structures are doing to actually see if the system is aligned to adapt to future changes. How does it work? It's a lovely model, and we all like models. But also it's not necessarily there is a fixed syntax. So this is an illustration of the key components of a system. So Stafford Beer brought this idea from cybernetics and kind of almost that idea that systems are organisms, to think of what are the functions and the systems within a system that operate them. And he found that there are 4 layers. There is the operations of a system, there is the coordination, there is operational control and strategy, and then 4 and 5 are quite glued together in a strategic and normative. But the example that we found there is really interesting. So it's Lassell using some concepts from Beer. So it's really interesting, very short paper on a football team. So if you think of a football team, you might have in a football club, sorry, you might have different teams like a youth team, a women's team, a men's team, and they all have their coaches. And you can think, what's the purpose of a football club? It's to win matches. So the systems 1, which are the blue ones, which are actually the teams, they are dealing with the operations of that purpose, winning matches and playing matches and things of the sort. But also a football club does not operate only on playing matches. You have a coordination system, which is, creating the regulations of the rules of the club, the regulations of the club, managing the space and the time between the teams. So this is a coordination aspect, a coordination system. Then you have the management of that coordination, which is a system 3. So these are different layers and performing different functions within a system. And above system 3, you have a system 4, which is looking at a strategic development. What is happening with the future? And the 5 is what's the identity, what's the normative, what the system actually is to define those things. And all of them are equally important because they play different parts within the purpose of a system. And what you have in the model, just going very quickly, is that the future here, this is a wider environment. This is the changing environment, this amoeba shape. What's important to emphasize there is that the type of environment that different functions of the system deal with are different. And that's how you can really see problems in the behavior of a system arise when the structure is not correctly fixed. I have a personal example from this. So in June, I was in Ghana as part of a project, and I was conducting a workshop on systems, and I gathered, luckily, people from very different spheres of the transport governance of the country. And we started drawing this, and very quickly we understood there were people in agencies in different spheres that were tasked to do the same thing and deal with the same environment. And it was very clear, and you could spot that moment, that is why you're having problems with the system in itself. So the key message for me is VSM should be used more as we have our systems becoming more and more complex and having more and more different organizations and different functions within it. And the more functions and the more subsystems we are dealing with, we need to be very, very clear about it, because it's very known that the structure of a system, that's the key message from the 2 ones that I've been talking about, system dynamics and VSM, that the structure of a system is equally important to the components inside it in the behavior of the system. So now I'm going to pass on to Bruce. Thank you, everyone. Oh, which one?
So that leaves one more technique to tell you about. My favourite, I think, and probably the most accessible, and as far as I know, I should be very pleased to be told that I'm young, at least you. So it's got a long title which should not frighten.
Bruce, one interruption, please.
Yes.
Your audio is very weak.
The audio is
closer to yourself.
I beg pardon. That's about as close as I can get it. How is that, Marcel?
Still very weak. It might not be on your microphone.
How is that, Marcel?
Still no change for the better.
How is that?
This is excellent.
Okay. You often wondered how many systems engineers does it take to get a microphone to work. So forgive me those who heard you. I was going to say this is my favorite technique. It's extremely accessible and in my view not used anything like as much as it should be. Although you may tell me you're using it and we'll be delighted to hear that. So this is the invention of Werner Ulrich, a Swiss researcher who's interested in emancipation and providing power to those who had little of it, particularly in the area of public policy. So let me make up an example that I think he'd agree is what he's talking about. Imagine that you are a Swiss resident and your canton has a plan to build a brand new luxury hotel on your mountain and a brand new road up to do that. You're not happy and you want to contest it, but the canton has paid a well-known consultant a large sum of money to do a very careful and thorough report, which concludes that on balance, the positives outweigh the negative. You are in a position of limited power. They've got the power, you don't. And Werner Ulrich wanted to do something about that. One of his observations, you can see his little triangle up the top right, is that boundary judgments are a way in which power is exercised. And by boundary judgments, he means what's included and what's excluded from what he calls the reference system, the situation or context, including facts and values considered relevant to a proposition. Once again, I observe there are elements of this that may make systems engineers feel a little uncomfortable. That's not quite our definition of system. Nonetheless, it's a useful definition of system. And once again, we see that although Herr Ulrich is still alive, still publishing on his website, he's quite an old man now, this seminal work was published in 1983. There are people in this room who were not born in 1983, I am certain. So it's really accessible. It's created for an ordinary person to use. And it's a checklist-based approach. So what you see there in 4 groups are 12 areas to look at, and where you simply ask, what have the authors of this policy included? And what do I think ought to be included? And the gaps, of course, are interesting. The technique just exposes the gaps. It doesn't tell you what to do about it. It doesn't make you do anything about it. But now when you go to the consultation meeting for this new hotel, you can say, oh, yes, your consultant did recommend that, but your consultant has left this out. If they had included it, they might come to a different conclusion. And you have a little bit more power than you had before. Okay? Of course, I mean, you've already seen. This may be originally intended for use by the people who are affected by a policy, but if you're creating some sort of policy in the very most general sense, and you wish to avoid accidental bias, then this checklist is useful to you. So it's not rocket science. Rocket science is Werner von Braun. Werner Ulrich's work is much more straightforward. And I mean, we've seen it used. One of our MSc students has used it to check whether she'd introduced unintentional bias in framing a problem, trying to improve requirements management. The output was about a table that covered about 3 pages and was genuinely produced some insights. I used to be a consultant. I never used it when I was a consultant, but I think that's a shame. I think I should have. For a couple of hours, I could have got considerably more confidence. And the man's website includes some very readable introductions, and in English as well, or in German. So there are the 4 that we want to talk about. On the chat, someone pointed out there's lots more out there. There is lots more. Someone's used general systems theory. That's a theory rather than a method. We think there's lots more. If you read Jackson's book, there's at least another dozen there. But these give you an idea, and they're the ones that we think are most useful. So I want to make some general observations. So I think the picture of the Birmingham hammer explains itself and is just a way of illustrating what is put by Maslow in rather more academic terms as the law of the instrument. If the only tool you have is a hammer, it's tempting to treat everything as if it were a nail. Okay? So, ladies and gentlemen, those of you who are systems engineers, beware, this law applies to you. If the only systems tool you have is systems engineering, it's tempting to treat everything as if it were a systems engineering problem. And more insidiously than that, if you're deeply embedded in the ideas of systems engineering, it is tempting if you attempt to apply one of these other techniques, to see it through the lens of systems engineering and to apply a diluted version of it. So, having made that personal warning, let's talk about some conclusions. So there are useful proven systems techniques. The ones we've talked about have decades of track record. Some have got a little forgotten, at least in the Rail SE community. I think perhaps we should be careful. If you go to the business school or the School of Social Sciences here at the university, you might see a slightly different picture. So let me summarize. Soft systems methodology, you might consider if you have multiple stakeholders who agree something is not right, but don't agree what is wrong or what needs to be done. Okay? Gives you a systematic way forward. And other tales as well, but that. Systems dynamics, you might consider if your system has complex feedback loops with delays, which are sufficiently complex that you may suffer from unexpected phenomena when you put it together. The viable systems model, you might consider if your problem is not just to deliver a system that does something today, but to deliver a system, and this would normally be a system with people in, that can adapt to a changing environment, can adapt itself. All right, that's not just be adaptable, but can actually adapt itself. And critical systems, you might consider if you want to check whether a proposition, either one you created or one someone else had created, has been biased by selective inclusion of things to consider. Okay? And there are others, but those are useful. So, final conclusion, SE is insufficient to solve all systems problems. Mike Jackson says, we do agree, and we believe the evidence shows that. And we go further, provocatively, to say that it always will be because it embodies a certain way of thinking about the world, and sometimes we need others. We're based in Birmingham, but we don't hold with Birmingham screwdrivers. We hold with using the right tools for the job. And we exhort you, the systems engineering practitioners, to familiarise yourselves with a range of other, it's a SSE. That just goes to show, doesn't it? I'm a systems engineer and I've fallen into my own trap. Other systems thinking techniques. No, not necessarily in great depth, but enough that you would recognise a situation where you might either want to learn more or hire someone who knew more about it. But do beware of the law of the instrument, okay? The value of those techniques is that they work in different ways. So when you find rich pictures, but a picture without semantics, or you find that Ulrich is using a different version of definition of systems, don't worry. It's like going to France and finding the postbox are a different colour. You know, don't complain. Enjoy it. It's part of it's part of the journey. And that, ladies and gentlemen, is what we had to say. I'm going to leave you with a slide, which you'll be able to see on the recording, with some further reading if you're interested. But we are really we have a couple of questions on the chat, actually, if Marcelo or someone would go through that. We're also interested, if you want to correct us in our assertion that there's a final thought. You can read that. That's a really good book. That's the thinner version, and it's on that list. We're also really interested if you've got examples of applying some of these things in, of course, railway environments. So if you scroll back, there are a few questions. There are also some comments, but I think it's the questions that
So shall I go in order?
Of course.
We've got one in the room as well.
So we'll start one online, and then we go in the room, and then we might do this. So, question for John. Coping with complexity, we try the concept of systems architect during design/engineering and systems integration during building. Are you familiar with that concept? And if you are, what is your opinion about that? So they try the concept of systems architect or architecture during designer/engineering of the system and systems integrator during the building. So the concepts of system integration.
So I am familiar with those, and I think that system architecting is an approach which is based in systems engineering. It's, if you think back to the diagram I showed of whether, is your worldview that you have a worldview which is a system of systems which is organized. So you have systems and subsystems. When you think about system architecting, you're thinking, I think, on the whole in that way. Whereas, so I think that could be used when you come to, once you've agreed. If the solution you agree through something like soft systems is a solution which needs which needs a hard system as a solution, you could architect it that way. I'm not sure that I agree that systems architecting as an approach is always applicable when you've got a soft systems type problem.
Thank you very much for your time today. It's definitely very insightful. Is it on?
Yeah, just keep close because
Close to my face?
Yeah.
Oh, excellent. Thank you very much. One of the things that leaped out to me and I was interested in, and it may actually give away that law that Bruce was talking about, that I am seeing this through a systems engineering perspective. But I was wondering, a lot of the examples that were given seem to be at kind of concept stage. So I'm thinking in life cycle models, and traditionally rail projects are a kind of waterfall V style life cycle. And a lot of the examples were at the very start of that V, identifying the problem and solutions. Is that kind of where you see these techniques being most applicable, or do you see them throughout the life cycle? Yeah, that was about it.
We've given you some very, very limited examples. The application of many of these techniques is very extensive. So when Marcelo was talking about the invitation to use VSM to run the economy of Chile, Stafford Beer flew out to Chile, and that picture of the space age control room is a representation of a control room that was actually built. So they really did, until the generals rolled in with their tanks, they really did try to, with some success, to run the economy of a country. I don't think you could call that concept stage, could you? So no, not really. There is masses of case study information for these, and most of it carries things through to implementation and beyond. Yes. Can I take the question that's out of order?
It's just
Sorry, my apologies for whoever's online.
Sorry, it's following on from this point as well. So does that mean typically you would only use one approach throughout, like start to finish?
That is a really good question. So we are adherents of Professor Mike Jackson. Okay, we think he's great, and we think he's on the right line, and he signed my copy of his book. He spends about 500 pages tackling that question. And the conclusion he comes to is that you mix and match. The trick is in how you mix and match, because they have different ways of seeing the world, actually some ways in conflict. And he recommends what he recommends is using multiple techniques, but allowing one to take the lead, but then changing which one takes the lead. So he's got really quite a complicated, but we think rather sensible answer to your question, I hope.
Could I just quickly add to that, if that's okay, before we go to question? What I think that's a personal experience, so Bruce and John might disagree, but it's the same way that in systems engineering we have the concept when we're modeling of viewpoints. For me, that's what I observed is that these techniques are trying to see different things in the system. So they're trying to do different problems of the complexity of the system, either if it's the board views behind them, or if it's the structure driving the behavior, if it's the structure driving adaptability. So they look at different things. So that's why we agree with Professor Mike Jackson that you need them all, because you need to look at the problem in various ways. So that is
okay. I don't disagree. Let's take how many have we got on?
We have done, I think, of questions, because there's been lots of comments and people answering questions. So I'm very pleased that the people online have been discussing things. So Bruce McNaughton asked, have you applied your techniques to management systems in example given ISO 22163?
I don't know what that is.
Yeah.
I'm sorry, Bruce. I mean, we and more importantly, lots of other people have certainly applied these techniques to management problems, but I have to admit ignorance of that particular standard. Sorry, Bruce.
So another question. They actually.
Could I clarify that?
Oh, sorry.
Sure.
That's for railway quality management systems. And it's based on ISO 9001. And the word
Right.
system in there is the interesting part, because all these techniques can apply to that, plus the systems engineering process. But I don't think people see that, actually. So that's my question.
Okay, so we have learned something from that. We're grateful.
Okay, thank you.
Thanks to Jonathan that just posted the link to the ISO 22163 standard, so everyone will have the recording, will have access to it. And Jonathan also sent a question that created a whole stream of debate, which is great. But I can bring this debate into the room. So, Jonathan questioning: is change management being incorporated into the systems engineering field? If so, how?
Oh gosh, well, I don't like to don't know twice in a row. Maybe John will help, but I mean, we don't own systems engineering. We teach it, but we don't decide how it evolves. We accept as individual members of INCOSE. That sort of feels like a question that ought to be addressed to INCOSE. John, can you think of anything else useful to say?
I mean, I think most systems engineering is applied when you're making changes to things.
Yeah.
Often, we have systems engineering, hard systems engineering, to use Jacqueline's approach, is often when we're changing hard systems. We're making changes to infrastructure or computer systems or products in some way. I always, I think of change management as being some of the management processes that you wrap around making a change. So I think actually a lot of what we've talked about, whether it's VSM, looking at how you design your management systems, or soft systems methodology, looking at how thinking about how different people interact with or view a system, an airport, for example, you might, so I think it is all related to what you would broadly call change management. Change management is a huge field.
Yes, I think that's probably probably the right answer to say is we don't know about systems engineering, but see soft systems methodology, because that's all about change management. And I think one more, and then with apologies to anyone who...
One more, because of the ones that I've seen, there was, I would still advise people in the room to go back and read the comments. They're fascinating. There was a really, really fruitful discussion. But in terms of question, so there's another Bruce, Bruce Lerner, so systems analysis is not only a systems engineering thing. In fact, existed separately from systems engineering. And this question is really interesting. When does a system problem transition into a systems engineering problem? That probably derives a little bit from what Chris was asking, but it's interesting.
Right. Because we have given you some views, some personal views about when the other systems thinking techniques are relevant. When systems engineering relevant, we'll have a go, and we'll see what other people say. I think it's relevant when you've got reasonable agreement on A, what your system is, and B, what you want from it. Surprisingly uncommon. Do you want, please? University.
You've basically summed up what I mean, we've discussed it. Yeah, I can't add much more.
Okay. So what we'll do at this point is to thank you, ladies and gentlemen, for your attention and for your questions. Apologize to anyone who online whose question we didn't get to, and close the call. And then those who stay here, I'll just have a quick word with you before we go. All right.